suppose I'm tossing a coin, and this coin results into two possible outcomes, heads and tails. I'm assuming that the coin would not land on the sides, and so only one of the two outcomes are possible. When I specify both the outcomes, I'm specifying the entire sample space. If I'm rolling a dice, if I'm rolling a single dice, then I have 1, 2, 3, 4, 5, and 6 kind of outcomes possible. Right? If there are, say, 10 people who are running a 100 meters race, then there will be the ways in which people would finish the race would be 10 factorial. The 10 factorial ways in which people would finish the race, right? If I am looking at, say, how long a particular component in a computer would last, then I would define that sample space as 0 is smaller than or equal to x is smaller than or equal to smaller than infinity, perhaps x. X is the amount for which that component would last, and x would be any number between 0 and infinity, right? 0 included. Because you can say that you started in the component burst rate, it didn't work at all. Okay? So that's 0 is the lifetime of the component. Okay, it didn't start. So if I'm talking about, say, battery of a mobile phone, you buy a new battery and it didn't work. So what was the life of that battery? 0.
But it
And
never stopped, so it will be infinity, right?
Huh?
If it never stops, that means it's infinity.
Technically it won't happen that it will not stop working. Someday it has to stop working because it's a component. A component has to stop working. That's why infinity. Someday, I don't know what day it will stop. Right. So these are examples of sample spaces. In terms of events, events are subsets of the sample space. Say, if I am looking at, say, success on a trial, then one of my event E is, say, event is, say, heads. Another event F is tails. If I say odd number of outcomes on a roll of dice, I'm rolling dice, so if I say odd number of outcomes, I define an event E which is 1, 3 and 5. I define another event F which is even number of outcomes, that is 2, 4 and 6. What I'm basically doing is I'm doing clubbing the events. When I say I'm putting odd events together, I'm creating a new event E which consists of all odd events, or new event F which consists of all even events. I'm combining events. So the whole point is, event necessarily is not the elementary event in the sample space. Event could be an elementary event in the sample space. See, there are two elementary events in the sample space. So I can construct an event by actually taking into consideration those elementary events, right? Or I can actually construct an event by considering more than one elementary events as an event. So I say I define an event that consists of odd number of outcomes, or I define an event that consists of even number of outcomes, right? So I can actually combine events and do this. There could be an event called as complement. Say, for example, in this case, the roll of dice, E complement is F. So complement is everything else but E. E complement means everything else but E. So all other possibilities but the possibility E are called as E complement. So in this case, in this entire sample space, what is actually happening is I have 3 odd events, 3 even events, elementary events. I constitute event E as all odd events. I constitute the event F as all even events. These are odd, these are even. So if I take a complement of odd events, then it's even events, right? That is F. That is the even. F itself is the even. So S complement is there's no event which is S complement. If I say that if this is the sample space for a row of dice, then if I want something which is not a sample space, then such a thing doesn't exist in this sample space, is called as null event. Okay, so I can actually do union of events. Say suppose I am doing an experiment, okay, in which my sample space is defined this way. There are 2 tasks. There could be a success on a task or a failure on a task. There are 2 tasks. So there are 4 possible events in the sample space. Success on first task, success on second task, success on first task, failure on second task, failure on first task, success on second task, and failure on both the tasks. Okay. So if I constitute an event, in such a way that I want all those events that have success on first task. Okay, success on first task. So success on first task is one event. Okay, success on first task, success on first task. Okay, so SS, SF, and I have another event which is success on second task. Okay, which is F, that is SS, FS. If I do something like if I create another event G, which is E union F. So either E is present or F is present. Okay, or both are present. Okay, which means this G will consist of SS, either S is present or F is present, it's present, SF or FS. So G is actually at least one success, and so G complement is FF, right? G complement is FF. I can have another event G which is E intersection F. Both E is present and F is also present. This happens only once. S, S. So G consists of S, S, that's it. So the only element that is common in both G and E and F is succession for both the trials. Okay. So when I say union, what I'm looking, so I can actually create event. I can create the event by unions or intersections of the events. These events are actually some kind of combinations of the elementary event. So event is not necessarily the things that are there in the sample spaces, but I can put them together, create events. I can do unions, intersections of events, and so on and so forth. Right? So this is how I can actually do events. The cumulative, associative, and distributive laws are applicable to the unions of events and their probabilities. So, well, that's not problem, like we can solve these the problems associated with unions and intersections by using cumulative, distributive and associative laws, which are fundamental laws of maths, right? Okay. So we're through with sample space and event. Just to reiterate, sample space consists of all, it's a set of all events, which event is a subset of a sample space. We know that subset can consist of all the elements, so subset is smaller than or equal to the entire set, right? Okay. Now we move to the next part, and that is probability. One of the common examples that we think of probability is tossing a coin. So when we toss a coin, often people say that probability that I will get heads is 1 by 2, given the reasoning that there are two outcomes that I am concerned about, heads or tails, and this is I'm asking a probability of one of the outcomes. This is not the right way of thinking, because implicitly we are also assuming that probability of getting heads is equal to probability of getting tails. But if they are not equal, then there will be a trouble. And so this is another intuitively appealing way of doing probability, which is called as empirical approach to probability, and that states that probability of an event E, is n limits to infinity, ne upon n. Okay, n limits to infinity, ne upon n. That is, as you increase n and as n reaches infinity, the probability is equal to number of times you observe n divided by number of times n could have happened, E could have happened, right? So ne denotes number of times you have observed E, and n is total number of times you have conducted that experiment, right? Say if I am tossing a coin, if I toss a coin 10 times and if 6 times I get heads, then probability is 0.6. But what I am saying is that n has to be as close to infinity as possible. So 10 is definitely not close to infinity, so I need to do this perhaps 500,000 times or 1,000,000 times to go closer to say something like 0.5. Suppose I take this experiment, say 500,000 times, 1,000,000 times I do it, 500,000 times, so close, very close to 500,000 times, I get, say I get 5 lakh 10 tosses. Okay, it's 500,000, close to 500,000, right? 5 lakh 10 tosses giving me heads, and 4 lakh 99,990 tosses giving me tails. Then the probability is something that is very close to 0.5, then it would be 0.5000 something like 1, right? Or slightly smaller than that. Okay, so in that case, it would go closer to what the true value is. There are two troubles with this kind of a conceptualization of probability. One, we do not know the n at which we should be stopping. Okay, how long should I conduct the experiment? 10,000 times, 1,000,000 times, 1,000,000,000 times, I don't know. Even if suppose I say I do it fairly large number of times, say I do this experiment 1,000,000 times and I get some probability. There is no guarantee that if I repeat this experiment again for 1,000,000 times, I would get the same value of probability. And so this is slightly a troublesome approach of dealing with probability. Now what then statisticians and mathematicians who work in the field of probability did is they did not really started talking about probability of E. Okay, they started talking about probability of instead of talking about probability, they started breaking down the concept of probability into simpler concept that can be used to construct probability. And this is called as axiomatic approach to probability. The earlier approach that we've discussed is called as empirical approach to probability. Now, this axiomatic approach says that if S is a sample space and E1, E2 up to E whatever En, Ek, whatever are the events in this sample space, then we can talk about En events. Let's say N events exist. Then we can define the probability of instead of defining probability of EI, the chance that the event EI would occur in a sample space S, we would look at smaller properties of this probability. So, given this, we can say they came up with some simpler statements which are called as axioms of probability. Axiom is a statement that is true by itself. No proof is required to show that this statement is true. It is self-evident kind of a statement. And so, generally in math stats, whatever we write, we have to give a proof of it. For axioms, you don't give a proof. They are called to be correct by themselves because they are correct. Okay. So one of the axiom, the first axiom is probability of an event E. Probability of event E will lie between probability of event EI would lie between 0 and 1. So probability of any event is between 0 and 1, both included. Okay. Second, probability of entire sample space is 1. Second, the probability of entire sample space is 1. Okay. Third axiom of probability is if I do union of if before we go to union, let's specify the condition. If the E1, E2 up to Ej, all events are mutually exclusive, that is, when events are mutually exclusive, EI intersection Ej for I is not equal to j, that is, I take any of the two events and I do the intersection, would be null event. So they are mutually exclusive. That is, as one event occurs, the other doesn't occur. If I roll a die, then if I get 2 on the dice, I can't get 4. All events on the roll of dice are mutually exclusive. Okay? If I'm tossing a coin and if I get heads, I don't get tails. So if A occurs, the B can't occur. If B occur, A can't occur. Okay? They're mutually exclusive. They can't occur simultaneously. They can't occur together. Okay? So if events are not occurring together, they're mutually exclusive, then the union of these events, I is equal to 1 to the infinity of union of probability of union of these events, EI, is equal to summation of I is equal to 1 to infinity EI. I take single event if I am doing the probability of union. If I am doing the probability of union, that is, I am basically saying E1 union E2 union up to say union of En. I am doing the union of these things. Basically, I should be doing probability of E1 plus probability of E2 plus up to probability of E n, right? If these are mutually exclusive, right? So this union would mean that I would be doing probability. So if I'm doing union of say odd events, okay, on a roll of die, I believe that all events are equally likely, and I'm doing union of odd events. That is probability of union of I is equal to 1, 2, 3 of odd events. So E, which is actually I'm doing union of. Actually, I'm doing union of 1 union 3 union 5, right? Which are mutually exclusive. If I get 5, I don't get 3 or 1. If I get 3, I don't get 5 or 1. If I get 1, I don't get 3 or 5. Which means that probability of 1 plus probability of 3 plus probability of 5. And if I know that they are equally likely, then it is 1 by 6 plus 1 by 6 plus 1 by 6, that is 3 by 6, that is 1 by 2, right? So the chance that I would get an odd event is 1 by 2 or 0.5, right? So this is the third axiom of the probability. By using these axioms, you can extend our understanding of probability, and then can actually do further solutions of problems associated with probability. Okay. Some simple things, if I do E complement, if probability of E complement, then if I want to do probability of E complement, it is probability of 1, no, not probability of 1, it is 1 minus probability of E, right? That is 1 is equal to probability of S, right? And probability of and S is equal to E complement plus E, right? Now, if I have to, if E is a subset of F, then what can we say about probability of E and probability of F?
Less than equal.
Probability of E is always smaller than or equal to probability of F, because E is a subset of F. When something is a subset, subset is E contains elements of F, or E is F. Subset is smaller set or equal to F, right? So if E is equal to F, then probability of E is equal to probability of F, right? But in all other cases, it is always smaller than probability of F. If I have to do probability of E union F, when I don't know whether they are mutually exclusive or not, then how do I do it? I do it by probability of E plus probability of F minus probability of E intersection F. Okay? Okay? Because when I am computing probability of E and probability of, I am adding probability of E and probability of F, then I am counting this intersection one more time. Say for example, if this is event E, this is event F, then when I say probability of E, I am counting this part. Okay? When I am saying probability of F, I am counting this part again. What is this? this is E intersection F. Both E and F are occurring. So I am counting E intersection F twice, so I am removing E intersection F from here. So how do I do probability of E union F union G? Solve this problem. Okay. People who have present in the previous classes have already done this, and also try and solve probability of E union F union G union H. Right? So try and solve both the things. It's pretty easy. You just need to come.
You did not give us the solutions of 4.
He did?
But that you work out, no?
Yeah, we worked
Pretty
out,
straightforward.
but we have to confirm it from you once.
So is there any formula or something? We have to do it
Is it something that you are convinced you've followed a logical process, then it gives the correct answer. Not followed, then it doesn't give you.
Because we did.
I told you what the logical process is. So try and solve it by using those.
We used substitution of values, and then there was a value
That's
like
too much.
48.
No, 1 second. It's the same as the previous one. And
You have to combine first and second to get the third, basically. Okay, so we are done with sample spaces and events, we are done with probability. Now we are going to random variables. Okay? Fine? So all those who have missed, I guess, are doing it pretty fast, right? And there's nothing much deeper to learn actually. In a sense, you have to read books to understand it at a better way. Ross is a good book to read, first course of probability, and so is the case with John Frant's math science. Okay, let's look at this concept, random variable. Random variable is an important idea in statistics. If we understand random variable well, we understand statistics reasonably well. Because unfortunately, when our trainings happen, we end up learning statistical tests without understanding what is the random variable that we are talking about, what is the distribution of a random variable. So we would quickly look at how do we think about random variable. Okay, let's take an example. Let's first define random variable. Random variable is a real valued function on sample space. Fine? It's a real valued function on a sample space. Right? Real valued function is any fx. Would be a real valued function. Okay? Now, let's take an example so that you understand how this real valued function gets applied to sample space and how do we get random variable. Okay, now say we are doing an experiment in the area of decision making. Okay, and we give 2 tasks to our participants to work through. Okay, this example is 2 tasks. Now on each of the tasks they would either fail or successfully make a decision. Okay, so now you have this sample space defined in following way. On the first task they are successful, on the second task also they are successful. On the first task they are successful, but they fail on the second task. They fail on the first task but do second task successfully, and they fail on both the tasks. These are the outcomes, likely outcomes. This is my sample space. These are the only things that will happen in this experiment. Okay, and failure means they give incorrect answer, or within the given time limit they do not give us any answer or do not give us correct answer. Is called failure. Success is within the time limit they give us correct answer. Right? So these are the only likely outcomes in all possible outcomes in this sample space. So sample space is a set that consists of all possible events. Right? Now what I'm doing is, generally in these experiments what we do is we assign them points. Right? So I say that you will get 1 point for success